Hey, my name is MathYou, and in this video we're going to talk about the fundamental theorem of calculus and finding exact area under the curve using integration. And for my students this semester in elementary calculus, this is our last hurrah because this is our last section of the semester. So I'm very grateful to have been able to create this content for you, and I hope that you have found it valuable. Let's get started on our last section. So we've talked about antiderivatives. We have talked about definite integrals, where we did integration and the result was a new function. And what we're going to be doing here is we are going to perform integration. You're seeing that stretched out S symbol, which actually is the first letter of the word in Latin for sum. And the sum we now have seen is the addition process of adding up the area of a bunch of rectangles. And by a bunch, I mean infinitely many. And what that does is it allows us to find the exact area under the curve. We're not going to go through the process of deriving and proving that we can actually use this great little symbol, the integral symbol, with a number at the top and the bottom of it. We're just going to use this tool right away. And I'm going to show you exactly what this notation means, but what this says is we're finding the area from A to B under this curve, and in order to do that we're going to integrate that function lowercase f, and we're going to get capital F, and then we're going to plug in the upper limit of integration into capital F, and then we're going to plug in the lower limit of integration into capital F, and we're going to find the difference between those two values. And that's this notation over here indicates that we're doing that subtraction process. And what that's ultimately going to give us is the exact area under the curve. The fundamental theorem of calculus does not require that our function always be greater than 0. The curve, can dip down below the x-axis where the y values are less than 0. That's allowed. And the fundamental theorem of calculus did not define the definite integral, it just provides a method for evaluating it. Let's evaluate maybe your first ever definite integral. In order to do this, I am going to integrate this function right here. So the integral from -1 to +3 of the function x plus 5 is equal to, let's integrate x plus 5. We get 1/2 x squared plus 5x. And I'm going to evaluate that from -1 to +3. And that evaluation process, now let me relate this back to what we were just doing up here. This is capital F of x. That was bad. This is lowercase f of x. So now I'm going to evaluate capital F at 3, and then I'm going to subtract capital F evaluated at -1. All right, let's do some arithmetic. We've got 1/2 times 3 squared plus 5 times 3 minus, so that's f of 3. Now we're going to subtract f of -1, so that's 1/2 times -1 squared plus 5 times -1. And we're doing arithmetic. We're in calculus, but we're doing arithmetic. So this is 9/2 plus 15 minus 1/2 plus 5. This is a -5, but we're subtracting it, so it turns into a plus 5. That looks good to me. Okay, 9/2 minus 1/2, that's 8/2, which is 4. 4 plus 15 is 19, plus 5 is 24. '24 is the area under this curve from -1 to +3. We did that using integration, and there's an x squared in there, and it turns out we got this whole number, 24. That's pretty impressive. Have a look at this. One, two, three, four, 5. 1, 2, 3, 6, 7, 8. So here's 5, which is the y-intercept, and it's got a slope of 1. So we're going over 1, up 1, over 1, up 1, over 1, up 1. And we're going down 1, left 1 to -1. And this creates a trapezoid. The height here is equal to 8, the height here is equal to 4, and this total distance here is also equal to 4. From -1 to +3, that makes a width of 4. How do you find the area of a trapezoid? The area is equal to the average of the bases. That's not how I wrote it in the previous video. I wrote it like this, the average of the bases. So we add them together, 8 plus 4 divided by 2, and then you multiply by the height of the trapezoid. Of course, I'm taking this trapezoid and I'm turning it on its side. So the height is the other 4, this 4. And we can reduce 4 divided by 2 makes a 2, and then 2 times 8 plus 4 is 12, so that's a 12 times a 2, which is, oh my gosh, it's 24. So you can use integration, or you can use formulas from geometry in order to find the area under this curve, which is particularly easy because this curve's not a curve, it's a line. When it's an actual curve, you definitely want to be using the integration process. So again, we found our antiderivative, and then we evaluated that antiderivative at the, or for the upper limit and the lower limit, and then we subtracted those two values, and we got our final answer. Remember, a definite integral is a real number, right? So when we're doing, or when we're finding a definite integral, we're going to get a real number like 24. You can read the rest of that. You can read the second bullet. You can read the third bullet. You can read the fourth bullet. And then we definitely want to be aware of these. This looks very similar to what we saw when we were first talking about derivatives. If there's a constant inside of the integration process, just like inside of the derivative process, you can factor that constant multiple out, as long as the constant is a number and not the variable that you're working with. You can, in number 2, effectively distribute the integration process over addition or subtraction. Number 3 says that if your upper and lower limits of integration are the same, then what you're doing is you're finding the area of a rectangle that has a width of 0. Therefore, its area is 0. Number 4, we're going to use this one. Number 4 says that if I were finding the area under the curve from A to B, I could find that area, or I could find the area from A to C, and I could add it to the area between C and B, and that would be the same as having found the area from A to B. Why would you ever want to do that? Why would you ever want to split it up like that? I'll show you in a minute. And number 5 says that you can switch your limits of integration. Instead of going from A to B, you can go from B to A, but if you do that, you're going to get the opposite of the area, quote unquote, that you would have otherwise. All right. Example number 2. Let's evaluate this definite integral. If you're not very good with finding your antiderivatives, this one's going to be a little bit tricky. I noticed that the stuff in parentheses in the denominator, if I take the derivative of it, I get precisely the stuff that's in the numerator. So I'm going to use u substitution here. I'm going to let u equal 1 plus x to the 5th power. Therefore, du is equal to 5x to the 4 dx. My substitution is going to occur here. I'm going to replace that stuff with a u. And this, with the dx, is going to get replaced by du. So let's rewrite our original expression as the... we have to make one other little modification. Now that we're working with a definite integral, well, are we going to substitute back? Yeah, we're going to. So the reason I'm fumbling a little bit here is because I could have us do something and then undo something, which I don't really want to have us do, but I feel like it's important that I should point it out to you at least once. These values over here are x values. What I'm about to do is I'm about to rewrite this integral as 1 over u du. There are no more x's. So I don't want to put a 0 and a 1 here because those are x values. I'd want to convert those x values to u values. How would I do that? Well, I could take the x value of 0 and I could plug it in here, and I could raise it to the 5th power and then add 1 to it, and I'd have a u value. Which is equal to 1. So I would take that 1 and I would put it at the bottom of my integral, replacing the 0 with a 1. And then the 1 that was my upper limit of integration, up here, I can take that 1 and plug it in also. U equals 1 plus 1 to the 5th power, that's equal to 2. And that 2 will be my new upper limit of integration. So perhaps if you are wanting to take notes on that, you could grab another color. I don't know how you're staying organized. I'm like nutso for being able to use all these colors. That's where those came from. Those are now, my limits of integration are now u values instead of x values. Let's integrate. What is the integral of 1 over, oh, that's 1 over u to the 4th power, sorry. What's the integral of 1 over u to the 4? It's the same thing as the integral of u to the negative 4th power, du. In order to integrate this, I believe it's called the power rule, we're going to increase the exponent by 1 and then divide by the new exponent. This is lowercase f. Really, this was lowercase f. This is also lowercase f. This is capital F. We're going to evaluate capital F from the between our upper and lower limits of integration. So here is where we change gears and start doing arithmetic. We've got to plug in these limits of integration. So let's recap. I did use substitution. Not only did I replace the stuff in my denominator with a u, I replaced my other stuff with a du, which you should know how to do. And what you've never done before maybe is you had to replace your limits of integration. The 0 and the 1, which were the original limits of integration, changed and became a 1 and a 2, because 0 and 1 were x values, but 1 and 2 are u values. And we got those by plugging in the x values and converting them over to u values. Once we had done all of that substitution and changing x values to u values, then we integrated. We found the antiderivative, which is this, and now we're going to evaluate the antiderivative at 2 and at 1 and find the difference between those. Let's see what it looks like. This is equal to plugging in my u value of 2. It's to the negative 3rd power over negative 3 minus plugging in the u value of 1 to the negative third over negative 3. This is equal to, well, it's equal to 1 over 2 to the third times the negative 3 that was already down there, minus 1 over 1 to the positive third times the negative 3 that was already down there. That's one way to do this. There are multiple ways to make sense out of the arithmetic that we're doing here. Ultimately, though, this ends up being 1 over negative 24. I'm going to write it as negative 1 over 24. And this is plus 1 over 3. The double negative here and here changed into a plus sign. Now I need a common denominator. That's a highlighter. That's a pen. There we go. Let's keep the 1, negative 1 over 24. And let's add multiplying 1 over 3. I'm going to multiply that by 8 over 8 so that this is now 8 over 24. Adding those numerators together, the negative 1 and the positive 8 makes 7 over 24. That is the area under the curve. That's a little intense. Even the arithmetic part of this, which is what's on the screen, was a little intense. I would say that going from here to here is new for you, and then realizing that this and this are equal to each other, that's new to you. Going from this line to this line is quite new for you. Everything after that was arithmetic. Really everything before this, you knew this is the only new stuff, right? You already know how to integrate and find antiderivatives. The only thing that's new is that we're now evaluating that antiderivative and doing a little bit of subtraction. All right, so you should be able to handle this. I'm excited for you. So in the previous video, if you actually watched the previous video, I mentioned that, and it was mentioned in the printed part of the notes, that you can add up all of these rectangles where your function value, your y values, f of x values, aren't always positive. And I gave this example of if you start out at a particular point and you travel positive 4 miles away from that starting point, and then you travel negative 4 miles, at the end of your journeys, how far does it look like you've gone? Nowhere. It's like a net change of 0. Oh, displacement is the word that I was looking for in the previous video. Anyway, it looks like you haven't gone anywhere. You went 4 miles out, you came 4 miles back. Looks like you've done nothing. You have a shower and throw on a fresh set of clothes, and it looks like you did no exercise. And in fact, you went out and ran or rode your bike or whatever 8 miles. So how is it that you're supposed to take the 4 plus a negative 4 and not get 0? Using absolute values. Okay, just use the absolute value of everything. Well, how am I supposed to incorporate that into the integration process? What this printed material right here says is that the definite integral from a to b of f of x gives the area below the curve and above the x-axis and between these two lines. But what if the function dips below the x-axis? All right, we're going to deal with that here momentarily. Use the definite integral to find the area between the x-axis and this over this interval. Yeah, that's fine. You need to integrate from 1 to 5, this function 2x plus 7, and you're integrating with respect to x. You can mimic the process that we did in the previous problem. I'll give you a little bit of a head start because the actual integral of this thing is x squared plus 7x, and then you have to evaluate it from 1 to 5. So you're going to plug in a 5 into here, and you'll get, well, let's just keep going. I'll just do it quickly. This is 5 squared plus 7 times 5 minus 1 squared plus 7 times 1. So this is capital F of 5 minus capital F of 1. And then it's arithmetic. 25 and 35 make 60. Minus 1 plus 7 is 8. So that's equal to 52. Awesome. I did that quickly. I'm just double checking to make sure I didn't make any mistakes. No, that's not a mistake. That's not a mistake. That's 25. That's 35. That's 60. That's a 1. That's a 7. That's an 8. Take it away. 52. Great. Okay. So there's an example that you can practice also. What I really want to do, since area is always non-negative, so the analogy of running 4 miles out and 4 miles back and it looks like you didn't go anywhere, that's where I am now. So what this says in this tan colored box is if part of your curve does dip below the x-axis, you're liable to end up with some negative area. And we don't really want to consider area as being negative. I really want it to look like I ran 4 miles out and 4 miles back, and I want to get an answer of 8. I don't want to get an answer of 0. The area under that curve that I just drew right there is 4. The area under this curve that I just drew is negative 4. I add those two areas together, I'm going to get 0. I don't want to get 0. What I want to do is I want to take the lower part of this curve right here, I want to take the absolute value of it so that I end up with this curve, so that this area also ends up being positive 4, so that positive 4 and positive 4, when I add those together, I get 8. Let's see how to make that happen. Sketch the graph, did that. Find any x-intercepts. There's one. Then divide the total region into subregions. Here's a subregion, here's a subregion. And the definite integral will be positive for subregions above the x-axis and negative for subregions below the x-axis. Right. This subregion down here that's below the x-axis is going to be negative. I don't want to add in a negative value. And so I'm going to make sure to account for that, or absolute value it, or negate it. Find the area of the shaded region. Okay, so here is our function, 4 minus x squared. We're evaluating from an x value of 0 to an x value of 3. Notice the x-intercept, the point where our graph crosses the x-axis. So I'm going to integrate, or I'm going to say that the integral from 0 to 3, those are x values now, of the function 4 minus x squared is equal to the integral from 0 to 2, so I'm just focusing, well, I'll draw it in a second. This area is being determined by this integral, plus, now I know that the area under my curve right here is going to be negative. If I integrate from 2 to 3 from my same function 4 minus x squared, this is going to be negative. And if I put a plus sign right here, I'm going to end up adding a negative area. And adding a negative is the same thing as doing subtraction. I don't want to do subtraction. I want to interpret it as though it's still a positive value. So, since this integral is already negative, I'm going to subtract the negative, thus causing a double negative, which will end up resulting in addition. Let's see it play out. This, by the way, taking my original interval from 0 to 3 and breaking it up into the intervals that go from 0 to 2 and then 2 to 3, is property number 4 that we saw earlier, where I said, why would you want to go and chop up the interval and turn it into these two different groups? Here's why you want to know that that is an option. All right, let's integrate. I'm going to keep my colors here. The integral of 4 minus x squared is 4x minus 1/3 x to the third. We're going to evaluate that from 0 to 2 minus the integral of 4 minus x squared is still 4x minus 1/3 x to the third, evaluated from 2 to 3. And I'm going to put this in parentheses. You could put this in parentheses if you wanted to. This is, it's not, never mind. All right, so I took my interval, I chopped it up into these two different pieces, and the part of my interval which is going to cause an area to be below the x-axis, I'm subtracting it so that the double negative causes it to be addition. Let's do some arithmetic. I've got 4 times 2 minus 1/3 times 2 to the third minus 4 times 0 minus 1/3 times 0 to the third power. All right, that's my first interval from 0 to 2 minus 4 times 3 minus 1/3 times 3 to the third minus 4 times 2. Is that going to fit? It's not. I've run out of space. Darn it. Minus 4 times 2. How am I going to make this? We know. Hello. Minus 4 times 2 minus 1/3 times 2 to the third. All right, so in red, I have the area that's right here, and everything that I've written in blue is this area down here. That second area, the one that's below the x-axis, is going to be negative. By subtracting that negative, it ends up being a plus. Arithmetic. We've got 8 minus 8/3 minus 0 minus 0. We could put all of this in these giant red square brackets. That will help these giant blue brackets make more sense, inside of which we've got a couple of subtraction problems. We've got a 12 minus 27/3 minus 8 minus 8/3. Now all of this is arithmetic, which is insanely boring, and if you're taking notes on what I'm writing, that's super. What's more important is that you realize why it is that I took this and broke it up into these two pieces. Reason being that the second of those two pieces represents a negative area. And since it's a negative area, that's why there's this minus sign. Subtracting a negative area makes it positive. Now, here is where I'm evaluating that integral. And then this integral is being evaluated here. And we have not been evaluating definite integrals for more than 30 minutes. So now I've got you doing a definite integral minus a definite integral, where the second definite integral is going to be negative. So I know that I'm sort of throwing you to the wolves on this one. This is a little bit like trial by fire, I think the expression is. So be patient with this, look through this, then go find another video that's got another example, and then look in your ebook and see how they work through a problem where they account for the fact that some of the area is negative. You're not just going to grasp this all at once right off the bat. Well, some of you will, but not all of you. Everything after that is arithmetic, though, so that's what we're trudging through at this point. This is now equal to 8 minus 8/3. 8 is the same thing as 24/3. We're subtracting 8/3 minus the 0, so I'm going to skip that. Minus, I've got 12 minus 27/3. That's the same thing as 12 minus 9, which is 3, minus 8 minus 8/3. That is 24/3 minus 8/3. 24/3 is the same thing as 8. All right, we're getting close, which is a good thing because we're almost out of real estate. 24 minus 8, 16. So I've got 16/3 minus 3 minus, now 24/3 minus 8/3. Hey, that's 16/3 again. Now I'm going to switch to purple because I'm going to blur all this into one now. I've got 16/3. I'm distributing the minus sign, which makes that a minus 3. And when I distribute this minus sign to this minus sign, that becomes a plus 16/3. So now I've got 32/3 minus 3, which is 32/3 minus 9/3, which is 32 minus 9. Well, 32 minus 10 would be 22, but I didn't subtract 10. I only subtracted 9, so I've got to put 1 back. So 32, 22, 23. That's 23/3. That is something. You want to take this problem and you want to go right back to the beginning and you want to copy down this information and you want to try to work through this problem again on your own. And if you get stuck, then come back to the video and let me work through it again for you so you can get caught up. And even once you get to the arithmetic part of the process, continue taking it slow because obviously there are a lot of opportunities to make mistakes in there. Excuse me. If you're using lined paper, use 2 lines for each of these fractions. Use a mechanical pencil so it stays sharp. Use really good handwriting, better than the handwriting that I've got here. Use every trick in the book that you can to stay organized on this one. And then lastly is an application problem, a word problem. This says that a company has found that its rate of expenditure in hundreds of dollars on a certain type of job is given by, now this function is being called E prime because it's a rate of expenditure. So that's the first derivative of the expenditure function, where x is the number of days since the start of the job. Find the total expenditure if the job takes 2 days. So we want to find the area under this curve from 0 to 2. So we're going to integrate e prime of x from 0 to 2, integrating with respect to x. That's the same thing as integrating from 0 to 2 the function 6x plus 4, integrating with respect to x, which is equal to the antiderivative of 6x plus 4 is 3x squared plus 4x, and we're going to evaluate that from 0 to 2, which is equal to 3 times 2 squared plus 4 times 2, so I'm plugging in the upper limit of integration first, minus, let's plug in the lower limit of integration, that's 3 times 0 squared plus 4 times 0. This is capital F of 2 minus capital F of 0. It's also capital E, but I'm using capital F because this is lowercase f. And then we found the, this is also lowercase f. And then we found the antiderivative, and this became capital F. That was the notation we used earlier in this section. If having these f's here is going to be confusing to you, get rid of them. You don't have to keep those. And then from there, it's arithmetic. We've got 2 squared is 4, 4 times 3 is 12, 12 plus 8 is 20, minus 0 is 20. So is our final answer actually 20? This problem says that a company has found that its rate of expenditure in hundreds of dollars, where x is the number of days, so hundreds of dollars. I would be willing to bet that this is $2,000. So if I'm typing in my answer online, I would probably type in 2,000. So the key words that you want to look for here is that they're giving you a rate function, and you're being asked for, so it's a rate of expenditure, and you're being asked for total expenditure. So you should have a note card that says something to the effect of, if given a rate function and asked for a total, you probably need to integrate. Okay? Something like that. Figure out a nice way to phrase it. Here we were given a rate function and we needed to find, and then you could put, for example, if given rate of expenditure equals e prime of x equals 6x plus 4, then total expenditure for 2 days equals this. Or if you're not using the specific problem, you could say equals this. Always try to match concept with process. As you're building your review packets in preparation for your last chapter test, as you're building a review packet for your final exam, always try to keep concept and process, the actual mechanics of working through the arithmetic, paired up. If it's not going to fit on an index card, find a better way. I think there is such a thing as a 2-ring binder. Maybe you have to think outside the box a little bit and find something that's made for creating recipes, where it's a 2-ring binder, but it's meant to have the rings at the top. And so instead of using a small index card, you can use an even larger index card. You might have to fashion something of your own to give you large enough pieces of real estate to write this kind of stuff out on. But keeping process and concepts matched up with, keeping concepts matched up with processes worked fairly well for me. So my hope is that that's going to work well for you, so that understanding allows you to move through, especially a final exam, a little bit more easily. All right, my friends. Nice hanging with you. Thanks so much for a great semester. If you're one of my students, if you're not one of my students, I hope my videos have been beneficial to you. See you around.